Hello everybody. Today we will talk about pure and mixed states. Probability plays a key role in quantum mechanics because we can only make probabilistic predictions about measurement outcomes. Measurement outcomes are always probabilistic predictions because we will not be able to exactly tell what is the measurement outcome. We will be the measurement outcome is one of the eigenvalues of the property that we are trying to measure, and the wave function is probabilistic. That means the measurement outcome is probabilistic in nature, and the total probability of all the outcomes, all the possible outcomes, is 1. Probability plays a wider role in science when we have only partial information about our system. See, the probability concept is relevant when we have partial information about the system, because then only we attach a probabilistic characteristic to that particular property that we measure, even in science also. For example, when we have a microscopic system and we have to use statistical mechanics to describe it, therefore there are two scenarios in which probability can be understood. Now, as we know that the probability that we are used to understand is due to the partial information about the system, but we will try to understand the probability also in quantum terms. That's why I'm saying here, therefore there are two scenarios in which probability can be understood with regard to quantum mechanics. So one is related to measurement outcomes. So one type of probability is related to the measurement outcomes, that with this probability this is the measurement outcome, and with this probability there is another measurement outcome. So this type of probability is due to the quantum mechanical nature of the system. But the other type of probability, other type of scenario of the probability, that is related to lack of information. So we don't have the exact information of the possible outcomes, or even the system. So therefore we try to measure, we try to define the system in terms of probability, and we need to interpret things using statistical mechanics. So there are two concepts of probability. One is the quantum mechanical probability, the other is the statistical probability. Let us compare these two types of probabilities. Let's say we have observable A associated with some physical property, and that the eigenvalue equation can be written as. So we have we have a property A, we have an observable, we can say that A, which is associated with some physical property that we want to measure. So therefore we can write the eigenvalue equation using this observable A. Now eigenvalue equation is given by the observable into ket un. This is basically the eigenstate. Lambda n is the eigenvalue, and this is the eigenvector associated with this eigenvalue lambda n. So this is the complete eigenvalue equation. Now consider only two. So to explain the two scenarios of probabilities, let us consider only two eigenstates for explanation purpose. One is ket u1, the other is ket u2, such that the two eigenstates are normalized with this inner product of u1 with itself and u2 with itself going to unity. So this defines the normalization, and also these two eigenstates are orthogonal, with the u1, inner product of u1 with u2 is 0, and lambda 1 is not equal to lambda 2. Now imagine we build a quantum state ket psi with linear superposition of these two. So imagine a quantum state ket psi that is defined using the two eigenstates as a linear superposition of these two states. So ket psi is given by C1 ket u1 plus C2 ket u2, where mod C1 square plus mod C2 square is equal to 1. So let's see what happens when we measure A. So when we try to measure this property A, and which is in state ket psi, so what will happen? As we have assumed, there are only two eigenstates and the two eigenvalues. So corresponding to lambda 1, which is the first eigenvalue, the probability of lambda 1 as the measurement outcome is given by Born's rule, which is the mod magnitude squared of the inner product of u1 with psi, and this is given by mod c1 square. So therefore, when the system is in state ket psi and we try to measure it, the state will collapse, and if lambda 1 is the measurement outcome corresponding to this eigenvalue, the eigenstate in which the quantum system will go after measurement is ket u1. And for corresponding to lambda 2, again the same thing, the probability of lambda 2 can be measured using the Born's rule, and it is given by mod c2 square. So when we do the measurement, the state will collapse to ket u2. So this is the eigenstate in which the quantum system will go if the measurement outcome is lambda 2, which is its second eigenvalue. So let us go to measuring framework again, but we will organize it in such a way that we will allow us to compare it with a different framework. So as I just described, there are two types of probabilities that we will consider. One is the quantum mechanical probability, the other is the statistical probability, statistical mixture of states or statistical probability. So let us try to understand the two measurement frameworks. First measurement framework is when we have the quantum system in state ket psi, and of course which is given by the ket psi is a quantum superposition of these two eigenstates. C1 and C2 are two complex numbers which are acting as the coefficients. Now we know that the system is in this state ket psi, and so therefore this state, and if we are considering only the quantum mechanical probability, it will be in ket psi. So that therefore this state of ket psi is deterministic. The system is made up of only one state ket psi, because the system we are considering is made up of only one state ket psi. Even if there are more eigenstates we assume, so ket psi will be 1, so which will be a linear combination of the eigenstates. The system is made up of only one state, which is superposition of ket u1 and ket u2, right? So therefore this system setup and the state selection step is deterministic in nature, which is ket psi. We know that the system is in state ket psi, but what will be the measurement outcome? The measurement outcome, when we try to measure this system, the measurement outcome will be probabilistic, because the measurement outcome can be eigenvalue lambda 1 or eigenvalue lambda 2 with probability mod c1 square and mod c2 square respectively. We have only one choice, that is the ket psi, that is about the state. So therefore the state is state selection is deterministic. There are two possible outcomes, lambda 1 and lambda 2, therefore measurement step is clearly probabilistic. Now this is first measurement framework in which only we consider the quantum mechanical behavior of the system. Now there is a second type of measurement framework, as I just described previously only, where we consider the statistical probability of the system. So let us create a new measurement framework. This framework is called statistical mixture of states. So there is this cell is showing the statistical mixture of states, because as we are considering only two states, so there are multiple copies of ket u1 and ket u2 are in this cell. So one of these states will be picked up, right? Our system is made up of many copies of states ket u1 and ket u2. To be precise, we have n1 copies of, let's say we have n1 copies of u1 and n2 copies of u2. So therefore the probability of state ket u1 being selected is n1 upon n1 plus n2, and this probability is mod c1 square, and the probability of ket u2 state being selected is n2 by n1 plus n2, and this probability is equal to mod c2 square. This step is different from the previous measurement framework step, where the state selection was a deterministic step. Now in this case the state selection is probabilistic step. Now once the state is selected, once either ket u1 or ket u2 is selected as a state, so therefore the next step, what is the measurement outcome, is deterministic, because if ket u1 is selected, of course the measurement outcome will be lambda 1. So therefore this step is deterministic, whereas the state selection step is probabilistic in this measurement framework. This is statistical mixture of states, and the previous was the superposition state, where the system is we are considering is only having the quantum mechanical behavior. Now that we have two frameworks, let us compare them. Both frameworks have a probabilistic step at different points of the flow diagram, as just I have described the flow diagram. In the first case it is measurement step, whereas in the second case it is the state selection step. It simply reflects that the fact that we have partial information about the state of our system, something that has nothing to do with quantum mechanics. So what I am trying to prove here is that in this case, in this statistical mixture of states, so we don't have enough information about the state of the system. So that means this step is probabilistic in nature. So therefore we have partial information of the system available. That is why the concept of probability is like n1 divided by n1 plus n2, or n2 divided by n1 plus n2 is coming. So this is because of the lack of the information about the system. This has nothing to do with the quantum mechanical behavior of the system, which comes from the measurement outcome, probability attached with the measurement outcomes. That's the quantum mechanical behavior. Now it simply reflects the fact that we have partial information about the state of our system, something that has nothing to do with quantum mechanics. And most importantly, this can also happen in classic, and this type of probability also can happen in the classical mechanics also. Therefore these two frameworks are fundamentally different. However, surprising thing is that from the point of view of performing a measurement, the two situations are completely equivalent, that they give the same answers. If you look at, so in the first framework the answer is lambda 1 or lambda 2, and in the second framework the answer is lambda 1 and lambda 2. So two frameworks give the same answers. It suggests that we can obtain results not by allowing rules of quantum mechanics in the first framework, but instead by having framework in which measurements are deterministic, and all that happens is that we don't have enough information about the system such that we don't know which of the two states, ket u1 and ket u2, will be picked up. That's the initial part of the second framework. Both frameworks are quite useful, although they apply to different situations. The first point is that there is no way we can avoid probabilistic measurements in quantum mechanics. The correct way to calculate measurement outcomes in quantum mechanics does require superposition state. That's the fundamental pretext on which the quantum mechanics is built. Now, a deep dive into quantum pure and mixed states. Now consider an original observable A with its eigenvalue equation, and a second, let's consider two observables now, A and B, and let's write the eigenvalues for the two observables. So let's say the system is in quantum state psi given by C1 ket u1 plus C2 ket u2, and there are two observables which we are trying to measure. So what we are doing is we are trying to find out the probability of measuring B. So we are trying to measure B with eigenvalue mu m. So what we are calculating here is the probability of measuring B in ket psi state, probability of this eigenvalue. So this will be given by, of course, the by Bond's rule with the magnitude square of the inner product, right? Vm is the eigenstate corresponding to this eigenvalue mu m. So this will be magnitude squared. This is Bond's rule, and this is the probability which will be given as per the Bond's rule, and this is given by C1 because if we replace ket psi with this expression, so we will get this, and if we expand the square we will get three terms, 1, 2 and 3, right? So this happens in the first measurement framework. But what happens in the second measurement framework? Let's see what happens in statistical mixture of states. So what is probability of ket u1, which is given by mod c1 square, and ket u2 is given by mod c2 square. Now we are trying to again measure the probability of mu m if the state is in if the system is in state u1, right? So how we will obtain this? We will obtain again by Bond's rule with the projection of u1 onto Vm. So that means this is given by the inner product, the magnitude square of the inner product of Vm with u1. And if the system is in state u2, it will be given by this formula, or given by this formula defined by the Bond's rule. Now this total probability of the total probability of what? Total probability of getting this eigenvalue mu m is either it is in state u1 or it is in state u2 is given by this two. Now if you compare this equation and if you compare equation 2, equation 2 does not have this extra term. This is twice real part of C1 C2 conjugate and inner product of Vm with u1 and inner product of Vm with u2 conjugate. So this term is missing in the second case. Now compare equations 1 and 2. Predictions are different for measurement of B in two scenarios. In the case of superposition state, one extra term is present. This term is called the interference term and is essential term. The predictions of quantum mechanics only agree with the experiment if this term is present. So this term actually defines the quantum mechanical behavior of the system, and the predictions that we will obtain if this term is present, this quantum interference is present, the predictions of quantum mechanics will only agree with the experiment if this term is present. Young's double slit experiment also includes this term. Quantum interference is actually related to the constructive and the destructive interference patterns that are formed in Young's double slit experiment. Therefore, the correct framework to describe quantum mechanics is the one corresponding to superposition of states. Second framework may lead occasionally to same predictions, but in general it fails. However, framework 2 is still let me just correct from here, is still important. Let's write it like this. Is still important when we don't have enough information about our system. Probabilistic step in framework 2 arises because of lack of information, but in quantum mechanical systems, the two probabilistic steps can be considered together. Hence, if we know everything about the system, the probability is a pure quantum. If we know everything about the system, it's a pure quantum effect, which is given by this. This is pure state. So that's how we will define the pure state and the mixed state. If we know everything about the system, the probability is a pure quantum effect. There is no statistical probability effect which will come into measurements. So this is a pure state. If we only have partial information about our system, then the probability in the system enters from two places. One is the quantum mechanical probability, the other is the probability due to lack of knowledge of the system. Probability we used to describe, which is termed as statistical probability. This probability which is related to the lack of knowledge of the system is termed as the statistical probability, which arises in the statistical mixture of states. So this has nothing to do with quantum mechanics. This also happens, of course, as I have just mentioned previously also, this also happens in classical world. So when this happens, we say that we have mixed state. Mixed state means we have the quantum mechanical probability also, we have the lack of information about the system also. That leads to mixed states. If we have only quantum mechanical probability and we have complete information about the system, that leads to pure states. So that's exactly the difference between the pure and the mixed states in quantum mechanical systems. Thank you.